Okay, so today I'm going to be answering the video question based around the MO diagrams, specifically explaining why H3C plus, H3C minus, and H3C star adopt the geometries that they do, and using the MO diagrams to explain that. Now, here it might be really hard to see, but I have these D3H and C3V MO diagrams. Now, excuse me one second. The D3H diagram represents CH3 plus. As you can see here, we have the bonding, the non-bonding, and we have a lot of the Mulligan symbols used to represent said orbitals. We built this earlier, I think it was Thursday we did all this together. And basically, when you follow the character tables, you can see which orbital corresponds to what, which of the Mulligan symbols get used, and how they all contribute to the MO diagram. You also see beneath that, we have the orbitals themselves that the Mulligan symbols occupy. And across from there, you get the in-between orbitals that they interact with. See here, there's a non-bonding on the A1 double prime, E prime, and then there's the anti-bonding as well. Now, D3, CH3 plus is in the D3H conformation. Because of the shape it's in, if that makes sense. So here, I'll draw out what CH3 looks like real quick. We have a carbon atom and 3 hydrogens on the side. The plus here. Now notice, here, this is in the, actually, I think I might have wrote this down wrong. Give me one second, sorry about that. This is in the trigonal planar model. Why? Well, because there's not another orbital here, because as noted by the plus sign. So, because there's not extra orbital, there's not an extra pair of electrons for the orbitals to occupy the orbitals. So, we have this symbol altogether. And it's trigonal planar because, again, 3 different atoms surrounding the central one. Basically, it has that conformation. And we can also see that from the orbital, the MO diagram itself. Following the character tables as well, we can see that trigonal planar molecules take a D3H conformation. And going through the checklist, we can see that this is in fact true. Conversely, we also have this, which the C3V MO diagram, which represents CH3 minus. And this is different from the CH3 plus in the minus sign. The minus sign is going to denote an extra set of orbitals, or a lone pair. So really, it's 4 altogether, but because it's not another atom, it's just a pair of electrons, it's going to have this conformation. In the, excuse me one second, the trigonal pyramidal conformation, which makes sense. This is a part of a tetrahedral a Vesper molecule because altogether there are 4 things attached to the central atom. The only difference is one of those things are just a lone pair of electrons. Now, comparing these two MO diagrams, we notice for one, sorry, give me 1 second. The first thing we notice is that the D3H, sorry, comparing these two, D3H is slightly lower in energy than C3V. And that makes sense due to the fact that there aren't as many molecules, or there is as many orbitals, not as much going on there. The trigonal trigonal planar molecule is by that nature going to have a lower energy. Now that comes to a good question comes by when we have, say, something like a CH3 star. What does this occupy? And because D3H is lower in energy, or its HOMO is so low in energy, the C3H is actually going to adopt this type of symmetry, more so than C3V. And that's because of the fact D3H is just lower in energy, more accessible. D3H is also has higher symmetry. Because the C3V molecule, CH3 minus is tetrahedral, it's not going to be as symmetrical. However, D3H, because it has an even amount of hydrogen atoms, has more symmetry involved around the carbon. Sorry, just give me 1 second. And yeah, that's essentially what it is. Because D3H is lower in energy and has higher symmetry than C3V, CH3 star is going to occupy this type of symmetry.